Hey everybody, let's jump right into one of the last vocabulary words that we'll use quite often to describe the motion of objects. Let's talk about acceleration. And we need to take some time with this because acceleration is another one of those words that we use one way in our everyday language, and we have to use it more precisely when we talk about physics. It has a much more precise definition in physics. So let's jump into it and see what that is. Acceleration is a vector quantity that's described as the rate at which an object changes its velocity. So acceleration is the rate of change in velocity. An object is accelerating anytime it's changing its velocity. So one of the first places that we might notice a difference from everyday language, we think of as acceleration is when something takes off and moves really fast, and it can be. But acceleration can also, something doesn't have to be moving fast to be accelerating. As long as the velocity is changing, then there's an acceleration. Now, when we're in our car, sometimes we think of acceleration when we go away from something, and when you hit the brakes, we think of that as deceleration. Well, in physics, it's all acceleration, but we said it's a vector quantity that's described by both magnitude and direction. So acceleration in a positive direction can be when something's speeding up, but we can also have acceleration in a negative direction. And if the acceleration is different from the motion, well, then we could have acceleration or deceleration, and that may be as clear as mud, but we'll straighten that up in another discussion. Now, there's a couple of kinds of acceleration that we need to pay attention to. There's constant acceleration, and then there's changing acceleration. Constant acceleration is what we'll look at mostly, but let's look at changing here also in this brief example. So here we have a table that gives us some velocities over time, and a change in velocity from 0 to 4. So that's 4 meters per second in 1 second. And we go from 4 to 8. That's 4 meters per second per second. 4 meters per second, and again 4 meters per second per second. So in this example, you can see that we're looking at an example of constant acceleration because the rate of change is staying constant. In this example over here, we have a rate of change of 1 meter per second, then 3 meters per second, and 1 meter per second, and 2 meters per second. So in this example, we have a non-constant acceleration because the rate of change of velocity is different between each interval of time. Examples in free fall are something that can be confusing for the reason that sometimes we look at the distance an object moves during an interval of time, and if we see a great change in that distance, then we think of that as acceleration, because in this example, look how much the distance changes from 5 to 20, and then 20 to 45, and 45 to 80. So if you look at this sort of change, we think, boy, that might be acceleration. But let's don't confuse distance in there. Acceleration is the rate of change of velocity over time. So here, from 5 to 15 meters per second is a change of 10 meters per second. Then from 15 to 25, again, is a change of 10 meters per second. 25 to 35 is a change of 10 meters per second, each one of those in a 1 second time interval. So the rate of change of velocity in free fall, as you can see here, is about 10 meters per second for every second. And so it is constant acceleration. Now finally, let's take a look at acceleration graphically and see if we can make a little bit of sense out of the graph and see how that leads us into a formula. Hopefully we'll see how that worked as it's worked in some other examples we've done. All right, we said acceleration was the rate of change of velocity. So we know we're looking at a slope. We've got the algebra here, and the slope of this line is what we're going to be calling acceleration. Remember the little symbol here reminds us it's a vector quantity. So let's take a look at our formula. So let's see, the rate of change is rise over run. So acceleration is the change in velocity, which is our y-axis, divided by time, which is the x-axis. So see how this formula kind of falls naturally out of our graph here, since we're talking about a rate of change. So what's our change in velocity? What we may remember from algebra is that if we're looking for the slope of a line, we look for y2 minus y1 over x2 minus x1 to get our slope. Well, looking here for acceleration, then, well, change in velocity. Well, that would be final velocity minus initial velocities. That's y2 minus y1 over. Now, we can't have we can't go backwards in time. Time's always going to be a positive change, so we can get away down here with just putting time in for the independent variable. So you see that kind of wraps it up kind of nicely and neatly here, that we've got these two expressions for acceleration mathematically. And if you'd like for me to, let's work a really quick example possibly of this and see how the math might work out. Alright, so let's say that we want to find the acceleration of some object that was traveling 50 meters per second final, and when we started it was traveling 0 meters per second, and this was all in a change over a 5-second interval. So what's our acceleration? So our acceleration is 50 minus 0 is 50 meters per second, divided by 5, oop, almost messed up, divided by 5 seconds. Make that a little neater, 5 seconds. So the acceleration of our object then is 10. Ooh, boy, here we go. What are we going to do for a unit here? So what are our units of acceleration? I want to take a minute with this because I could just tell you what it is, but that's relatively unsatisfying because it's much better to see where these units come from. So bear with me and let's figure out this unit right here. I'm going to clear this out. So I'll tell you what, down here at the bottom, let's remember that we're trying to find, let me just write it. We're looking for the units for acceleration that were 10 what? We've got meters per second over seconds, and that looks strange. So let's see if we can make a little better sense of that. All right, getting rid of this. All right, so let's do some math just with our units. Well, we've got meters per second. That's our rise. And then seconds for our x-axis. So meters per second divided by seconds. Well, let's take a look at this. Meters per second. Let's change some colors of things so that we make a little more sense of it. That's meters per second divided by, well, let's make this a fraction also. So if we put it over 1, then we've got both of these set as a fraction. And what I hope you may remember is that when you're dividing by fractions, it's the same as multiplying by an inverse. So here's an equivalent statement. We've got meters per second, and we can multiply that by the inverse of seconds over 1, which is 1 over s. And so this is starting to look pretty slick now. So meters times 1 is meters, and seconds times seconds is seconds squared. So there you have it, nice and neat, wrapped up in a little bowl. Your common units of acceleration are meters per second squared. So if we look back down here at our example then, let's drag it back over here maybe where we can even see it a little better. Alright, so that acceleration that we had earlier, meters per second is the same as meters per second squared. And how cool is that? And we'll wrap this up as a quick discussion of acceleration. And there you have it.